We're going to look at a whole new way of graphing in this video. So what we call this is polar coordinates, and how it works. So normally, we would graph something like we would move over on our x's and then however many for our y's, right? Like say the point 30, right? We'd go there, 30. Or likewise 0, 3, or anything in between, such as like, I don't know, go over 2 and up 2, we have 2, 2, right? And of course negatives as well. So how this works though is we're looking at two things. I'm going to tell you an angle that I want you to go, and then I want to tell you the distance. So what do I mean? Like, for instance, this point here, right, 2, 2. I know that the angle to get to that point is pi over 4. It's a 45-degree angle. Now the distance, I don't know off the top of my head. We'll take a look at what that is. But I want to know how far from here to here did you get. And those two things combined in order to graph that point. So I drew the line for reference, but the line wouldn't be there. In polar coordinates, we need r, which is the distance, which we've used that before in trig, the distance on a graph, basically the hypotenuse if I were to draw a right triangle, right? So we need that, and then we need this angle theta. So for instance, let me draw a new set, and we'll use some of those values I did up there in a minute. If I had given you 2, so I said to graph this point, 2 comma pi over 4, then I am telling you to look at the angle pi over 4, which is 45, right? And then go 2 units out. And one way to, let me get rid of that angle there. One way to look at that is if I had a bunch of concentric circles here. So if I did the unit circle, right, 1 unit out, kind of using that for reference. Okay, that's right here, that point would be 1 pi over 4. So I have 2, so let's go another unit out. Okay, so this point here is 2 pi over 4. I get bad about labeling, but that's okay. When we're dealing with all units here, right, kind of makes sense where I'm at. So to graph that point, we are there. Now, to make a correlation between these other 2 points, 3, 0 and 0, 3, those I could actually kind of just see, right? If I were to ask you to graph 3, 0, this would be exactly the same as the Cartesian coordinate up there, because the radius, right, r, I went over 3 units, r is 3, and then the angle is 0. But that point 0, 3, whoops, that's 0, 2, let me go one more, 0, 3, oh no, I forgot I have a setting where it erases everything that was touching there, my bad, there we go. Okay, so this point 0, 3 on the Cartesian coordinate system, the Cartesian is just the fancy way of saying graphing xy, right? But in polar, we need r theta. So r is still 3 because the radius is 3, right? The distance is 3. but the angle is pi over 2, right? It's a 90. So this point is now 3 pi over 2. Okay, whole new way of graphing. I'm not graphing these on a grid anymore. I'm actually graphing more like these concentric circles, and just because the couple examples I gave all had whole numbers because it's easier to visualize, it's not to say you can't have a rational number here that's not whole, right? Like I could go 2.5, right? That I'm just somewhere in here in this circle. Alrighty. Next, what we're going to do, so that's the idea. That's how you would graph a polar coordinate versus a Cartesian coordinate. But let's wrap up, like, how do you get from one to the other? So if I have a Cartesian coordinate, for instance, this 2, 2, we never finished, right? Like, what is that on the polar? So this 2, 2, we're going to convert to polar. Well, we knew that the angle was pi over 4, but you can't always just eyeball it, right? For instance, I'll do the point 1, negative 3. So we'll do two examples here. All right, 1, negative 3, right? That's down here. So I don't really know for sure what that angle is. It's somewhere in the 4th quadrant, right? This angle here to get to there, somewhere in the 4th quadrant, but I'm not sure what it is. So we have to use some trig. And using r and theta, there are a couple things. So there are a couple formulas we have been using, but now we need to go full circle and use them in a different way. So let me first write these formulas. So we have the fact that, well, sine theta is y over r, right? Cosine theta is x over r. Tan theta is y over x. We're going to use these in various ways in a second here. The last thing we know about r is the Pythagorean theorem, right? We do know that x squared plus y squared equals r squared. Since r, we could draw any right triangle to get a visual of r, right? Now, we're going to do both of these examples here, but I want to show how the formulas we use can be used differently as well. So let's also take like this 2 pi over 4 here, and let's convert that to Cartesian coordinates. And then let's also just do one that we know the result, the 3 pi over 2. Okay, to verify. And again, this would work for any graph, any value I give, you can use this system. So we're going to do 3 and 4 first, honestly, because they're a bit easier. And what do we need in a Cartesian? We need x and y, right? We need x and we need y. And then we have our point, x comma y. Looking at above, I know that I could solve for y in sine and say y equals, not that it matters, but it's more common to say r sine theta. Right? If I multiply r on the other side, y equals r sine theta. And therefore x is r cosine theta. So if I have r and if I have theta, it's as simple as plugging it into that formula to see what x and y come out to be. So let's actually do number 4 first. I'm going to choose a different color. Because I know this one, right? We should get 0, 3. So y equals r, so 3, right? This is r, this is theta, multiplied by sine pi over 2. So on the unit circle, sine of pi over 2 is 1. So we get y equals 3 times 1, which is 3. Okay. Now x is r cosine theta, 3 times cosine pi over 2. Cosine of pi over 2, remember it's the x value, so at 90 degrees is 0, so 3 times 0, which is 0. So we do in fact get 0, 3. Do the same thing for 2 pi over 4. So y equals 2 times sine pi over 4. Well, sine of pi over 4 is root 2 over 2. Y equals 2 times root 2 over 2. So y is the square root of 2. Okay, x is going to come out to be the same thing because we do r cosine theta. And cosine and sine both have root 2 over 2 as the value. So the 2's cancel and we get root 2. So that coordinate 2 pi over 4 is root 2 comma root 2. Alrighty. Those are the easy ones. The other one isn't, it's not terrible. But sometimes, like, I made up 1 comma negative 3 off the top of my head. Sometimes we're going to need technology, so let's check it out. Let's do r first, because that is the easy one. Okay, so we'll start with number 1. So 2, 2. So that's x and that's y, right? So 2 squared plus 2 squared equals r squared. So 4 plus 4, 8 is r squared. So r is square root of 8. And in this case, well, in all cases, I'll explain how r can be negative at the end, but for now we're going to always create r to be positive. All right, so we get 2 root 2 for r. Now we need theta, right? To get polar coordinates, I need r and I need theta. So how we do that is we use tangent because I know y and x. At this point, though, we could use sine or cosine because we know both x, y, and r. So it really doesn't matter, but oftentimes, you could do r first or you could do theta first, and I'll explain why you might switch. So tan theta equals 2 over 2. So where's tangent theta equal to 1? Well, that is at pi over 4. Right, whereas x and y the same. Or it could be 3 pi over 4, right? But looking at this one, I know I'm in quadrant 1. The value is 2, 2. I'm going to stick with pi over 4. But again, I will explain how that answer, we could get something different. So 2, 2 as a polar coordinate then is r comma theta. So we get 2 radical 2 comma pi over 4. Okay, that is our answer. That is equivalent to that point in polar coordinates. 1, negative 3. All right, so this one, like I said, you're going to need a calculator. I kind of just winged it off the top of my head. That's all right, though. So x squared plus y squared equals r squared. 1 squared plus negative 3 squared equals r squared. So we get 1 plus 9 is r squared, so 10. Again, I'm going to stick with the positive r. All right. And now tan theta equals y over x, negative 3 over 1. So where's tangent theta equal to negative 3? And my calculator closed. So go ahead and put that in your calculator while I do. Tan inverse, right, of negative 3. And I'm in degrees. Tan inverse, negative 3. Negative, so we get negative 1.24 about. Okay, so 1.24 radians. And this, is this on the unit circle actually? No, it's not. Okay. Negative 1.24 radians. So let's take a look at that. If I went negative, right? So theta's there, and then I went a positive r, I am at this correct point. Okay, so this does work. This is a great example actually to wrap up this video and show how negative, what if r is negative, and we just saw what if theta is negative. So again, r theta, negative 10, and in radians, it doesn't have an exact answer, so we just do that. Okay. Let's, since I have this polar graph here, actually I don't need to move down. I'll stick with green. Let's graph something like negative 2 pi over 4. Okay, what does that do? So we still go in the pi over 4 angle, right? But instead of going outwards of 2 in this direction, we just go in the opposite direction. So this point here is negative 2 pi over 4. Now what if I asked you to graph, which we kind of did above, that's okay though, graph 2 negative pi over 4. Well, now I go negative angle, right? Negative pi over 4 is there, and then I go outwards 2. So I'm here. Okay, what if I made both of them negative? Negative 2, negative pi over 4. Well, I do this negative angle like I did, but now I go in the opposite direction for negative 2. So this point here is negative 2, negative pi over 4. But all of these, like even our original 2 comma pi over 4, can be written differently, right? Like, well, I know that this angle to get here is 3 pi over 4. So I could call this point as well, I could call it 2 comma 3 pi over 4, and therefore these are equivalent. There is more than one way to write a polar coordinate, where in our Cartesian coordinate system, right, if we have 2, 2, there is only one point. That is definitely only one point given. However, one point in polar coordinates can be written in a couple different ways. Well, and in fact, if we continue to add 2 pi, right, I could write any of these infinitely many ways by just creating coterminal angles here. All right. So likewise, one more example, you know, we have this point here. Instead of doing pi over 4, right, I could do 5 pi over 4 and a positive 2. And this one here could be 7 pi over 4, positive 2. So it depends, right? Usually we do like positive r's and positive angles, and you can imagine where when you graph these negative ones, how a positive one could look as well.